Now we're going to talk about volcanoes and earthquakes. So volcanoes are basically created in three different places. The first place is a divergent boundary, and these are your more gentle volcanoes because what happens is these plates will move away from each other, and then they will gently create new land in between, and that will create in creating that new land. It's a gentle process. It's not completely gentle. There is still some seismic activity, but relatively speaking to other volcanoes, it's pretty gentle in its process. The second type of boundary is a convergent boundary, and this happens a lot with the Pacific Ocean. Basically, the North American and South American plate, as well as the Eurasian plate, and these plates over here are all squeezing in from every direction on the Pacific plate and pushing it. And basically, that convergent boundary, the Pacific plate's getting pushed under every plate around it, and therefore it's getting destroyed. Now, in that process, because there's a lot of heat and a lot of friction, it creates more violent volcanoes. And that process of creating those violent volcanoes are basically from the destruction of that plate as it's being pushed underneath. The third place where volcanoes are created are places like here in Hawaii. And basically what happens is in the middle of the plate underneath, within that convection current, you get what's called mantle plumes. And those mantle plumes will push up in the middle of the convection current and actually push through the crust at one point. Now, the interesting thing about this is as that gets pushed up, you get your entire convection current that goes around here, which causes the plate to move and it causes the plate to slide because the convection current is pulling it around. But then you get these mantle plumes, and this mantle plume actually pushes up in the middle of the convection current and pushes up into the crust. Well, while this crust is being pulled to the side, the plume is pushing through, creating a volcano. So what happens is it creates a volcano here, then the crust slides and it creates another volcano, the crust slides and another volcano, another volcano, another volcano, and these volcanoes basically create islands. And Hawaii is a great example of this because you get a string of volcanoes as this crust gets moved along with it. This plume is pushing through and creating those islands in that chain. Earthquakes are the next thing. They're a sudden and violent slip between two plates at a transform fault boundary. Now, because these plates aren't really smooth as they push past each other, they have such a violent jerk between the two, and it causes a lot of shaking. The point at which the shaking occurs most is that focus. That's a point deep into the crust where the slipping actually occurs. But that slipping causes vibrations that then go up to the surface of the earth. And at the surface of the earth, we have what's called the epicenter because that's where humans are, and that vibration is going to be basically this point right here. The epicenter is where most of the destruction is going to be, because as this earthquake moves out, it starts to dissipate. The waves get more spread out, but at this point right here, all the waves are concentrated at one location, which causes a lot of shaking and a lot of destruction. So earthquakes basically produce three types of waves. You got your primary wave, your secondary wave, and your surface wave. The primary waves, which we call P waves, are the fastest. So they arrive the first, and they're the least destructive. They're a longitudinal wave, which means they can basically go through any type of material. As long as there's a medium there where there's a solid, liquid, or gas, P waves can go through it. But they're pretty fast, so they don't cause much destruction. The secondary wave is a transverse wave, and because of the properties of a transverse wave, it can only go through solids. Now, it's not as fast as the P wave, so it arrives second, and it causes a little bit more damage than the P waves do. The last wave is the surface wave. The surface wave arrives last. It's a circular wave, so it includes that back and forth motion by the longitudinal wave as well as the up and down motion by the transverse wave, and this is what causes the most destruction, and it only occurs at the Earth's surface. So the destruction is caused mostly by the surface wave than it is the other two types of waves. So this is a seismogram, and basically what it does is it shows you the P wave, the S wave, and the surface wave, and how much time passes between each one. And you can see that the amplitude of each one increases, which basically means that as the amplitude increases, so does the destruction and how much it vibrates the Earth. Now, if you look at a P wave is a longitudinal wave, which means it has compressions and rarefactions, and that vibration back and forth is what creates that wave. And then you get your secondary wave, which has the up and down. So you got your crests and troughs, which you can see here has a little bit more more movement than would ordinarily be with a P wave, which could cause more destruction. And then your surface waves have a combination of both of these that get your up and down and back and forth motion, which creates even the most destruction. Now, because these seismic waves go through the Earth, not only do they go on the surface, but P waves and S waves actually go through the Earth as well. Now, because they're waves, waves have certain properties. Waves move through a medium, and as they move through a medium, they will actually refract when they go from one medium to another. So you can see right here that the yellow line represents the P wave. The P wave will actually refract when it goes into the outer core. It'll also refract when it goes into the inner core. This is how we know what is inside the Earth. The S waves can only go through solids, which means it can't go through the outer core. So you get a range on this side of the Earth where you don't see any S waves because it can't go through the core. That's how we know it's a liquid, because those S waves can't go through it. Now in here you have you get a refraction again, so you get P waves that come through, and because they refract, we know that the inner core is a different material than the outer core, so we know it's a solid rather than a liquid. You also notice that in the mantle that these lines curve. The reason why they curve is because the mantle itself, as you go down, is getting more and more dense, and that means that the medium itself is changing, which causes the refraction of each of those waves. So the interesting thing here is because of the refraction of the P wave, we also get a blind spot for the P wave where there's no P waves here because they're all refracted down rather than being able to go straight through. So based on these high accuracy of these seismic waves, we can actually determine what is inside of the Earth because of the properties of the waves as well as going through the materials that they go through. A tsunami is actually an underwater earthquake. And this underwater earthquake, if you were to be right here above where the earthquake occurred, you probably wouldn't feel too much other than just a little bit of a ripple. You probably even confuse that for a regular ripple of what you'd see by the wind blowing onto it, onto the ocean. So you see little ripples, and usually tsunamis aren't that harmful until they start getting to places where you have a continental shelf. Because if you can imagine, all of this energy is spread out over a deep part of the ocean, it doesn't really cause a lot of damage. But then it gets close to an area that has a continental shelf, and that continental shelf, what it does is it amplifies it squeezes that energy into a very small area, which then gives you more energy and pushes the water up and out of the ocean. You can kind of think of it as if you have a cone that you yell into, kind of to amplify your voice, that cone will spread, or take your voice that's spread out over a larger area and confine it to a very small area so it's a lot louder. That's essentially what happens with a tsunami. It takes all that energy and it focuses it down to a very small area, which causes those big waves, those tidal waves that come in and splash onto cause very tall waves that come in and hit the land. So the activity that we have called analyzing seismic wave activity, we're going to be kind of going through how we determine the epicenter of an earthquake based on the lag time between P waves and S waves. So on the worksheet we have this chart right here, which shows Austin, Portland, and Bismarck. And basically the first mark represents the P wave that hits each of these cities. So each of these cities know that there was an earthquake that occurred somewhere because a P wave hit them. And then sometime later the S wave hits them. Now this difference in time is caused by the fact that P waves move faster than S waves. So as the P wave moves through the Earth and gets to each one of these cities, the S wave is coming behind it. Now the further away the city is from the epicenter, the further amount of time, the more time, which we call lag time, between the P wave and the S wave. So based solely on this, you can see that Portland is going to be closest to the epicenter because the P wave and the S wave are closer together than the other two cities. Bismarck's going to be the furthest away because the lag time is much greater for those. So in looking at the lag time for each one of these, we see that Austin has a lag time of 300 seconds. Now, in our packet, we have a graph that says that 300 seconds gives us a distance to the epicenter of 1,875 kilometers. For Portland, the lag time is 240 seconds, which the chart gives us 1,500 kilometers. And then for Bismarck, it's 340 seconds, which the chart gives us 2,125 kilometers between Bismarck and wherever that epicenter is. So starting with Austin, we know that Austin has a distance of 1,875 kilometers. Now we don't know what direction the epicenter comes from, so if we draw a circle that is 1,875 kilometers away, then we know that the epicenter is somewhere along this circle. We just know how far away the epicenter is. We have no idea what direction it is. So the epicenter could be along any point on this entire circle, which basically means an infinite number of locations that we could have the epicenter. The epicenter could have come from the north, it could have come from the east, come from the west, come from the south. Who knows, because we only have the amount of distance away that it is. So then we go to Portland, and Portland says that, well, the epicenter is 1,500 kilometers away from us. Well, we draw a circle for Portland all the way around, and we see that Portland's circle intersects with Austin's circle at two locations. So that means that Pierre could be an epicenter as well as San Diego, because because those 2 points are both 1,875 kilometers away from Austin, as well as 1,500 kilometers away from Portland. So in order to really refine this, in order to get down to one location, we need a third point. In Bismarck, what it does is we get the distance for Bismarck, which we found to be 2,125 kilometers, and then we draw our circle around there, and we can see that that will intersect at a very specific location. So the spot near Pierre is not the epicenter is near San Diego. And that's because the distance of the epicenter from each one lines up right there. Now this process is referred to as triangulating, because what it does is it basically takes three different locations, and then you figure out where that epicenter is based on those three different locations, and then since we know how far it is away from each one, then it can be only one possible location, that is San Diego. So this diagram, we see the direction that the plates are moving as well as how fast they're moving. You can see that the North American plate and the African plate are actually moving away from each other kind of slow. The purple represents a very slow movement. But then the Pacific plate is being essentially being destroyed, so it's being pushed a lot more. So the North American plate and the Australian Indian plate, that is pushing on the Pacific plate, basically making it move pretty fast and destroying it in the process. So let's compare the sun and the earth. The sun and the earth both create heat that gets to the surface, and what we're really trying to do is we're really trying to see how heat gets to the surface of the earth. So both have a nuclear process. The sun has a nuclear process of nuclear fusion, and then the earth has nuclear fission that creates heat. Now the earth actually has heat left over from when it was created, so that heat, in addition to nuclear fission, is being transferred to the mantle. Now the sun has a process of radiation. As the heat comes from the core, it radiates outward through the radiative zone before it gets to this outer layer here. Now the outer layer for both of them, the earth and the sun, have a convection zone. So the heat is transferred from the core into the mantle, and you get convection currents for the earth. The heat is transferred into the radiative zone and then into the convective zone, where you get convection currents there. And then by process of conduction, the heat transfers to the surface. Now, but since we're talking about the surface of the earth, and that's pretty much where we stop for the earth, the sun, however, radiates its heat to the earth, and that's how we get heat from both sources, from the earth and from the sun, and they wedge between it pretty much at the surface of the earth.